Cool.
Hey guys, welcome to a new lecture of string
So
theory. Today we're gonna do like relativistic strings,
we're changing,
which basically
cosine
just
by 2
means
pi, and it's repeating.
doing a different
Then
gauge.
we know that this
So we're
part
gonna
has to be equal to
throw
2,
off
so
all the
multiple
work
of
we've
2
done
pi,
so far
and then we
and
get
just change the gauge for sure.
Delta is equal.
No, we're actually gonna use like a generalization of the gauge
has to be equal to 2
we've been
pi
using so far, and
times m. Okay. M
let
is
me
just
just
an
get it
integer,
started and
integers.
you'll understand what I mean.
So cool.
Cool.
So now,
So
if we go back
last
to the full expression,
2 lectures we've been
but in
doing
zero, we're gonna
relativistic
go
strings, or I think 3 lectures.
times 0.
We derived the
We
fundamental
have
string
this.
equations, which were the wave equation, and we also had
Sigma.
2 constraint equations, and we also had the boundary conditions. So that was cool. And we also have conserved currents, which you saw we had the Lorentz current, we had the Orsi current, and using Noether's theorem, you can get all types of currents by
gonna
using a
choose
symmetry.
M1.
So if you have a symmetry in your system, then you automatically get a current. Cool. Okay, so today we're gonna do a couple of things. First,
So what do you think happens
rotating
if we don't
string.
choose
We're gonna do an example.
M1 here?
And we're gonna find a new parameter.
Thoughts?
A parameter called the slope
What
parameter.
happens if, like,
And
why we
this is a
chose
very
A1?
famous parameter in string theory.
Basically,
It's
because
usually
it's
called the
gonna
Regge
recover
or Reggie. I don't know how to
the-
call it. I'm gonna call it the Reggie slope, like Reginald Roach, but it's not Reggie, but it's another Reggie.
The sigma
Reggie slope.
in 0
Cool.
and sigma 1.
So then
Like
the second
between
thing we're
this
gonna do
interval.
is like on relativistic strings, which is introducing a new gauge, and we're not gonna get to put in the like the solution of the equation in a very nice form. We're gonna do that next lecture because there's not gonna be time. Yeah, you can see it's only 2 things, but these are gonna take a while. So let me get started. Cool. Okay. So, oh, by the way, next class I'm not gonna be here. I'm gonna be traveling, so this is gonna be a video for next class. Next class, basically, we're gonna do quantum mechanics. We're gonna do quantum field theory, and we're gonna start with classical field theory and then quantize that. It's not gonna be as hard as it sounds. Like, there's just 3 or 4 rules that you need to know all the stuff you need to know before getting into quantization of string theory. So it's good. Cool. Okay, so far we only had one dimensional parameter in the string, in our string theory, or in the relativistic strings, that it was the tension. So we want to change this parameter to the most usual one, just for convention. Most things are written in terms of the slope parameter, so we want to see what is the slope parameter. And this is just the proportionality between the angular momentum in units of h bar and the energy square. So I'm gonna show you where this slope parameter comes from, and like where does it appear, what is it equal to, everything about slope parameter, by introducing you to this example. So consider we have a rotating string. So this is just a string that is stretched. This stretch L halves in one side and L halves in the other side, so its total length is L. It's going with an angular speed of omega, and also, yeah, we have like the endpoints. The endpoints are just rotating. Cool. Okay. If you remember from last lecture, the only thing we had to determine in order to solve this system was the f function, like the fu that we saw last class. So basically, to determine this, first we know already from just the diagram how the coordinates are working. So for example, the 0 coordinate behaves in the following way. It has an amplitude of L halves, and it has this functional form. Cool. Okay, so that's like most of the information we need, because we already know like what's the form of the string, like how the string is behaving. So like that's the main thing to solve. We know that. Cool. So then we can apply what we knew of f. That is, f is equal to t0 at t0, and this would be just equal to this. So here I'm just doing boundary conditions. We know that f ct, or this could be u, is equal to x t, but at 0, like at one of the endpoints. There was like a minus sigma if you wanted to see like the whole expression, but right now we're considering only the endpoint that is at 0. Cool. And then yeah, that's all we need. We can also put this in terms of u. In terms of u, it would be L halves cosine omega t. Then we have omega u c sine omega u c, and here u is just defined to be ct. Cool. Okay, so now we also know that f is quasi-periodic, so it's quasi-periodic. And notice that f, like this thing, is periodic. Like we already knew that in order for f to do something, it has to be quasi-periodic, but periodic is a better condition. So if f is periodic, then this has to be true. Think about it. Why? I'm gonna ask this in class. Why? Why, guys? Why b naught has to be 0? If you let me remind you, well, that's a good reminder. No, this one. What was b? It was here. I don't expect you to remember this or top of you. Okay, let me copy and paste this. Cool. Let me put it here as well. Cool. Okay. So if you remember, we had this, and we had this parameter b that was for quasi-periodic stuff. So every time there was like a period, our string was changing in another direction. So it was like repeating, but repeating towards a direction, and we call that speed. So why should it be 0? Because a periodic function is not quasi-periodic, so it means that this term doesn't exist. That's the answer. We'll see if someone catches it during lecture. Cool. Okay, so now that we know that, we can write f in this form plus 2 sigma 1 f u. And if we do the following change of variables, I'm gonna do a very weird change of variables. Trust me, it's gonna make sense. Cosine of x, sine of x. Cool. So here I defined x to be omega u over c, and then delta to be omega over c 2 sigma 1. This is just a period. It's just like how much, like the length that it takes for one period to repeat. So cool. So then this, if you know how periodic functions work, then this implies that the frequency behaves in this way. Cool. So this implies, because we're changing cosine by 2 pi and it's repeating, then we know that this part has to be equal to some multiple of 2 pi, and then we get this expression, because delta is equal, like delta has to be equal to 2 pi times m, and m is just an integer. So cool. So now if we go back to the full expression but in 0, we're gonna go in times 0. We had this sigma plus f minus sigma cosine halves sigma 1 0. Cool. Now we're gonna choose m1. So what do you think happens if we don't choose m1 here? Any thoughts? What happens if, like, why we chose l1? So why did we choose m equal to 1? Basically because if you look at this, you have sigma 0 here and sigma 1 here. If we had chosen 2 or 4 or other number, then whenever sigma is equal to sigma 1, then this wouldn't be minus 1. Like, it wouldn't give the right shape that we have of the string. Cool. So that's the reason we're choosing m equals 1. You want to think about it, it's just the first mode. So it has this shape, just the first mode. Cool. Okay. Also, it allows us to write, we have the frequency here, the expression we had before. Sigma 1 T0 over E. Here I'm just replacing the expression for sigma 1. Cool. We can take a derivative of f And we're going to impose now the condition that this has to be unitary. So this was the condition. And basically this is going to tell you, like, if you do the dot product, this is going to be 1, the factor that's going to appear. So you're going to have this square equals 1, which means L equals 2c over omega, or the length, which is the same as writing 2 sigma 1 over pi. This comes from here. And you can also write it in terms of energy and tension. And from these two, we get the following. That the endpoints have to move at the speed of light. Why? Because this is, you can think as a radius. So you think, if you remember this formula from mechanics, then this tells you that the endpoints have to move at the speed of light. Cool. We confirm that. And okay, now we know here that the length is smaller than for an static string. Like for a static string, we had that the length was just E over T naught. Like for our first example of string theory. For a rotating string, we have that the length is smaller. And if you want to calculate what is the energy is just going to be T naught L pi over 2. Cool. And as you can notice from this expression, like these expressions, as you go higher energy, then your angular velocity decreases. And why is this? What do you think is this? The answer is that as the length grows, like as we have a longer string, then the angular velocity has to decrease in order to keep the endpoints to be at the speed of light, because we know that this is a condition for relativistic strings to work, that the endpoints have to be to the speed of light. So cool. So then our functional form, or f, it's going to look like this. Cool. And we can plug it back and get the final solution. I'm going to skip, let me just copy and paste the solution because it's a lot of copy and pasting. Cool. Here. So this is the solution for this calculation. Cool. This is how the string behaves. If you can see here, it's periodic, and also the amplitude goes changing depending on where you are at the string. Cool. From this part, I'm gonna go to the nodes, and I think it's better to go part by part to get a big explanation. So cool. Okay, now that we have like the functional form of our example, that was like the main thing. I think it was chapter 8 that we calculated. And now we can calculate the angular momentum. How do we do this? If you remember, we had the charges from the Lorentz charges that we calculated. And one of them, especially like the L3, was equal to the M12 charge. And if you remember, we derived what the form of M12 is, or like for a general M mu nu, what the form was. And this is equal to this form. Cool. So here we need to calculate this, and we already have x. So cool. So if we want to calculate the momentum density, we already had a formula. We just have to take a time derivative, and we can find it here. Cool. And if you replace this expression up there, you're gonna find this, that the charge equals this, and eventually it's gonna be sigma 1 squared T naught 2 pi c. And if you replace that here, then that just gives you a dependence on the energy. Here I made like a very quick substitution that T0 is equal to, where's this? But that's sigma 1 equal to E over T naught, as we always do. And this is gonna give you the following expression. Cool. So here is where you get the proportionality between J and E squared. And we call this constant proportionality um, alpha, or we call it the reg slope. Reg slope. And just equals to this. Or if you want to have the tension is equal in terms of the reg slope. Cool. And one can also show, I'm gonna do this derivation because this is gonna take a bit, that the string length can also be written in this form with the reg slope. I might put you this maybe for homework 5. I still have to publish homework 4, which I'm missing. So I will publish that, and then yeah, cool. So now we have the dependence on this famous parameter. And now we are gonna go towards light cone relativistic strings. Here we're gonna introduce a new gauge. We're gonna generalize the static gauge. So far we've been using the static gauge, which is this gauge. And now we wanna generalize it to better gauges to get simpler equations in order to quantize it. So this is gonna be a bunch of just generalizing the static gauge. So first, let me put you just the formula. That's gonna be a linear combination of the string coordinates, and it's gonna equal to some constants times the tau parameter. So here we're going back a couple of lectures to where we introduced the static gauge and also the sigma gauge, and like forgetting about those two, and now reintroduce it again. So here, n mu is gonna be a constant for vector, and lambda is gonna be a constant. So we can choose, like if you choose the normal vector to be 1, 0, 0, 0, we just get back the static gauge. Like just try it, and then you're gonna get back the usual x0 tau sigma equals c tau. Also you have to choose lambda to be c, but yeah, cool. That's how you get the static gauge. But in this generalization, basically what the generalized gauge means, like this choice of linear combination, it's gonna be the following. Imagine you have a string worldsheet. The string worldsheet is this blue stuff, and you have some hyperplane that is determined by the normal, by this n mu that you're choosing. So imagine you have the hyperplane that is normal, it has a normal. So this hyperplane has this equation. Notice how I wrote, instead of the big X, I wrote the small x, because this is just hyperplane, this is not a worldsheet. We save the big X for worldsheet coordinates. But here is just this is just a hyperplane. So if you intersect the hyperplane with a worldsheet, that's where you get the string at a time tau. And that's how, like, the picture you have to have in mind for this generalized gauge. So cool, you just imagine hyperplanes intersecting like at each timestamp. And yeah, that's how this new gauge is gonna work. Cool. Okay, consider that this, also you have to notice that this gauge condition is not Lorentz invariant. Why? Can I pause for 3 seconds? Why is not Lorentz invariant? It's pretty easy to see this, since if we change coordinates, then this is gonna change. So clearly, under any coordinate transformation, this hyperplane is not gonna stay the same, so this gauge is gonna be different. Cool. Okay, so now we're gonna do a bunch of simplifications with this initial formula. First, let me take out the units of lambda. I'm gonna just put a constant. This constant is gonna be n times p, and p is, let me put units to lambda, and I'm gonna introduce another constant. So we showed this last lecture that n times p is constant. This is just a 4 vector. This is just scalar, and we can you can always put one constant towards next to another constant, and then call the whole thing a constant. You can call this whole thing lambda. So we just decompress it into 2 other constants. Cool. That's the only modification we did. And yeah, we traded the lambda for lambda hat. And from now on, we're gonna use, this whole trade was in order to have tau and sigma to be dimensionless. So if you notice here, the string coordinates has units of length, and we're gonna have this parameter that's gonna cancel the units somehow with momentum in order to get length units. I'm gonna see what units lambda has right now. And we know that the open strings are attached to d-branes. So in order for this quantity to be conserved, we're gonna require n to be chosen such that we conserve the momentum. So that's the way we're gonna choose n. So that's good. This is just to keep up the n times p, n dot p conservation. Cool. Okay, and by unit analysis, we can also determine that lambda hat is speed over force. You can see this from just having the momentum there and having a dimensionless. This is dimensionless now, and we have length. So if you do the unit analysis, you find speed over force. And what is the speed over force that we have clearly in our theory is the speed of light and the tension. And this can also be written in terms of the Regge slope, like this. Cool. Now, right. Let me introduce natural units. Natural units is something where we set every fundamental constant of the universe to 1. In this case, h bar, c, and kb equal to 1. And this is just a convention. Like, technically, you're not setting them to 1, you're just hiding them and then putting them back when you need them. Usually we don't put them back unless like we absolutely need to. So this allows you to keep track of only one unit. You get rid of length and time, so we can keep track of only mass or only length or only time. But most people only do mass. That's like the most common, and this is just a convention. So cool. So here, if you notice, now that the speed of light has units of length over time, we can set it to 1. That this means that length and time behave the same way. So anything that's on units of length is going to have the units of time and vice versa. And from h bar original units, we can do simplification. We know that L has the same units as time, so we get ml. And then from there we get just 1. So m has inverse units of length, or length has inverse units of mass, and time also has inverse units of mass, therefore. Cool. So mass is inverse to length or time. Great. So if we go back to our slope parameter has units of 1 over T naught over the tension. Because why? Because we set 1 C equal to 1, which is equal to units of mass or length over mass, or the same as length square or 1 over mass square. And you can do this with any single unit full quantity. You can like put their units in terms of only mass units. And this is like very, very useful for doing anything. So that's good. Cool. So now we had our result that the length of a string was equal to this. And now we can just put it like this. This is a very, very beautiful and famous formula that the length of a string is just going to be the square root of the slope parameter. And yeah, you're going to see this everywhere, so just remember it. Cool. And also we can simplify the Nambu-Goto action and just put it in this form. The only thing that we change is the constants, and any C or H bar that were in this action just disappear. It became 1. So this is even more famous, yeah. This is like how usually as a theorist you would write the Nambu-Goto action. And cool. So now in our gauge, we had this lambda hat constant. We're gonna just choose it to be the slope parameter. Why? Because of unit analysis, we can do that. We know the lambda hat has to have units of what is this? Speed over force, or also known as units over c over t naught, which is the same as having units of just radius slope, which is a dimensionless quantity, or the dimensionful quantity. Cool. Okay, so we can do that, and then we just set equal to 2 for convenience. You're gonna see pretty soon. Alpha. And this works for open strings. So this is going to be the gauge, the tau gauge we're going to use for open strings. Now it's a more complicated formula, but essentially it's just in the same spirit as we did with a static gauge. Now we're just using hyperplanes instead. So then we can assign an associated parameterization for sigma. And for sigma, you remember we required each piece of the string to have the same energy density. So now instead of that, we're going to require this quantity to be constant, which is the density times like dotted with the normal vector. So which is going to be the same. Like that's essentially, if you replace the normal vector by 1 0 0 0 0, it's the same thing we had before. So the static gauge, we're just generalizing it. Cool. And also we're going to require a new thing, that is sigma is going to go from 0 to pi. This is also going to make the numerics easier. You can like put sigma in any interval, because you can always like map, there's infinite numbers in any interval of the real numbers. So that's cool. And with these conditions, we can claim that if this equation holds, that's our sigma parameterization. And why this makes sense? Because we're making sigma be proportional to the momentum carried until that point of the string. So essentially what we're doing here is taking, if you remember from our picture, we had like some string, and the sigma parameterization was just telling you where you are along the string. So you're just parameterizing, integrating over the momentum until you get to some point of the string. Like, what is the momentum until you get to this point? So that's this parameterization, and dotting it with n. So that's why it makes sense. And another way to see why it makes sense is you can just take an infinitesimal interval. By this I mean just taking the sigma. And if you take the sigma, you can see that that the momentum is going to be proportional to the momentum density. And also you see that this quantity n dot momentum density tau is a Worley constant, so it's constant on tau and it's constant on sigma, which is great. It's a quantity that we know, like, it doesn't matter where you are, it's gonna be the same. It's just forever constant throughout the worksheet. Why? Because we know this one was already sigma independent. We had shown this a while ago. I remember where, but we had shown that. And also we had shown that this one is tau dependent during last lecture. So cool, we can combine those two things, and this is just a, these both constants are worldsheet constants. Cool. So now if you look at the equation of motion, which is this that you should have memorized at this point, you can tattoo this, like, you can tattoo this to your forearm, or wherever you want. Cool. We just dot it with n, and this is gonna give you this equation. Cool. So in this equation, you notice that this is 0. Why? Because we showed that this is a Worley constant, so it's going to stay the same. And now we have this. So now we know from this equation that this quantity n dot momentum density sigma is independent of sigma. Cool. And also, if you remember, like, here I'm just putting the definition of p integral. Like, this is just the integral over this sigma. And we know that this quantity has to vanish at the endpoints. And from the boundary conditions, we know that, where am I? Here. Cool. So this quantity has to vanish, boundary conditions. And for open strings, for now. For closed strings, we can do the same, like the same procedure we did. Let's have parameterization, and the only change from here to here is there's a 2. That's the only change. And for the tau parameterization, there's no 2. That's the only change, because we changed the interval. We changed from 0 to 2 pi, so that's why you get an extra 2 pi. And cool. So in summary, these are all the tau and sigma parameterization we're gonna use. You have that this works for closed and open strings. For closed, I didn't show it, but it's a similar argument to just having boundary conditions. Then for the tau parameterization, you have this parameter beta that's 2 or 1, depending if it's open or closed, and it just tells you how it's going to be parameterized in tau. And then you get also this condition for sigma parameterization, that is depending on the integral of the momentum. So we're just doing the same, like, same density at each point, or at each part of the string, but using this integral. Cool. And if you take a derivative with respect to sigma of this, then you get this relation between the momentum density and p, which is the same that we got before. It was here. Cool. And it's different for open and closed strings. For open is 1, and for closed is, or for open is 2, and for closed is 1. Great. So now we can derive the fundamental equations. So using the general gauge, the equation stays true. Like, we already had this equation, and it's going to stay the same. There's a long derivation of why you show this is true again. Basically, is getting the momentum density expression. You remember that long, huge thing that we had, and we can use these equations to show that this stays the same. So that's cool. And then we can use this condition to simplify our current expression for momentum density in tau, for momentum density tau, and then from here we can also use this condition to put it in terms of beta and momentum density. So then we get this. Cool. And then by the tau parameterization, we can also substitute this. And then we find this constraint equation. This is one of the constraints equations. So we just summarize two of them here. We can add them and subtract them. We already did this last lecture, but with the static gauge, but we can get a similar equation here. So this one looks much simpler than before, and we can also simplify hugely the momentum densities like this. And then just plug it into the equation of motion, you get this beautiful equation that is just a wave equation. So these are the fundamental equations that we're gonna use. Cool. And now we can find a solution. We're gonna do mode expansion. So now I'm gonna go through the same procedure that we solved last time. First we start with an ansatz. If you remember last time we did only the space components. So why we did all this huge generalization is in order to be able to get all components, also time. So first we start with our ansatz, that is, you have two functions, two waves, one is going this way, one is going this way, and you can add them together. And now we're gonna do the same as before. We impose boundary conditions at 0 and pi. Now we're not using sigma 1, now we're using pi. Cool. So at 0, we can find the same as before, that g is just gonna be f plus some constant. But if we do at sigma equals pi, then we're gonna find something different. Now we're gonna find that f, like the derivative, has to be periodic with a period of 2 pi, which is essentially the same, because then the function has to be quasi-periodic. Cool. So then a periodic function, if you remember from Calc 2, you can always put a periodic function in terms of a Fourier series. So these are Fourier series. We're basically introducing some offset, some constant offset. And then we had our base functions, which is cosine and sines, and some coefficients. Cool. So that's a Fourier series for any function. This is just a general function. And we can also integrate to get, oh, this is the derivative, by the way, because we had that condition for the derivative. So now we can integrate, and then we get, what is the function? F. So if we plug it back to x, then you get to this form. This is already a pretty nice form, like we already solved a very general solution for relativistic strings. The only thing we're considering here is that we have free endpoint boundary conditions, which is the same as saying we have a space filling the brane. And a space filling the brane was just having a brane that is like that allows you to be free, so it's extending completely in whatever is your ambient space. Cool. Okay, so now we're gonna do some redefinitions. First, let me change these coefficients into this form. So this form, I'm just doing reshuffling, like using the Euler identity that tells you that e to the I in tau is gonna be cosine of n tau plus I sine of n tau. Cool. So that's what I'm doing here. And you put it in this form. And then you can also take out, like redefine all these constants into these new A coefficients. So these A coefficients have like a very hard, or like not hard, but like lengthy definition. Like you have to move stuff around. So I'm just gonna show you why they have to be this. So if you take the complex conjugate of this one, you're gonna get this, as you can see, the complex conjugate of each other. And they're gonna be dimensionless. So in order to take out the dimension, we're just defining these parameters here. So you can look at it for 1 second and it makes sense. Just go, we're just redefining constants. Cool. Okay. Remember that A is dimensionless. So now let me look at the first mode, or like F1, that was this constant that we had here. If you take the momentum density, then you can calculate it. You're gonna get this quantity plus some cosine and sigma, which is gonna vanish when we integrate for the momentum. We're just trying to find the momentum, which is the integral of the momentum density. And all the cosine and stuff terms vanish. So then we just get this. So we can make F1, like the first term, to be 2 slope parameter times the momentum. Cool. And we can just rename this to be, we can call it an offset or an x sub naught for a vector. We call it zero mode. So this is an even more famous form that is in terms of these a coefficients, and we can make it even better. So more notation. Now we're gonna define this is just a bunch of string theory notation. We're gonna define this alpha coefficients. So alpha 0 is gonna be this. If you notice, this is gonna be here. Here, no, here, right? Cool. So it's gonna be there. Wait, what? Let me check something. Oh yeah, okay, that's good. That's okay. Cool. Okay, so these other alpha parameters are gonna be just like ladder operators, but you don't know what a ladder operator is, so forget what I said. But if you know quantum mechanics, which I'm gonna explain next lecture, you know where this is going. But for those who you haven't taken quantum mechanics, then basically here we're already defining constants. We had these a constants, and we're just putting times some square root of n. We're just trying to make expressions look nicer, easier. And we're also defining this alpha, but with negative coefficient. So here, the negative coefficient just means that we're doing the complex conjugate. And if we do the complex conjugate, then also you can show that, like, you can see very clearly that if you do the complex conjugate of a normal one, like of this, you're gonna get the opposite with a negative index. So that's good. And we just replace all of this stuff into here. You get this huge expression, or in a very nice and simpler form, you can combine these two terms into one, and then we get this. How do we combine this? We use a trig identity, if I'm not wrong. Oh no, here we just combine everything because we added up from n minus infinity to infinity, but without 0. So cool. And this is like the super famous solution of relativistic open strings. Relativistic open strings with Newman boundary conditions. So absolutely every string is free to be wherever they want. And cool. And just for record, let me calculate these two quantities. These two quantities are just the derivative and the time derivative and the space derivative. We're gonna need later, but let me just put it there for now to show you that we can calculate it. Cool. So we can also add up and subtract this and put it in a nicer form. And nice. So essentially the result today was that we got a closed solution for a relativistic open string with Newman boundary conditions, which is already a lot. You from here we're gonna see how you can get a mass spectrum. You can also get something called Virasoro modes, which is gonna have more physical meaning. So this is like the most physical equation. I'm not gonna go into the details of what this means yet, because I'd rather quantize it first, like get the mass spectrum, and then show you where is the string theory coming. So that's cool. So next week I'm gonna be off. I have grad school visits and a conference for APS Global Summit, but I'm gonna give you 2 lectures in a video. I know you love videos. I don't think you do, but we'll see. I'm gonna try to make them a bit better, like more explained in depth. Usually the last videos I'm making it like an hour before the lecture, so that's why the videos are going a bit fast. But it's in like the videos, whenever I make videos when we have actual in-person lecture, it's mostly for people that didn't attend to lecture and just can see the lecture. I have someone talking about the material, and so that's cool. But next class we're gonna get the Lycon spectrum, so we're gonna show how there are particles that are coming out of the relativistic string, which we haven't quantized it yet, but there is some mass spectrum, some stuff happening. I'll show you what this means. It's not gonna have that much physical meaning until we quantize it. So in order to quantize anything, we need quantum mechanics, and we also need quantum field theory. So we're gonna do this next class. So essentially next class is gonna probably be a 2-hour lecture video. So yeah, that's gonna have a bunch of content. If you have seen quantum mechanics, you're gonna skip this part. If you had quantum field theory, I wouldn't recommend skipping this part because we're gonna use different notation and we're gonna work in the Lycon gauge, which essentially just means we had so this is what the Lycon gauge means. Wait. I'm not gonna tell you absolutely anything, just that. Cool. Okay. With that picture in mind, after the spring break, we're gonna start quantize the open relativistic string, which is the fun stuff. And after doing like so many derivations and praying for seeing actual physics and seeing particles come out of nature, now we're actually gonna see stuff. So after spring break, we start with quantizing the open relativistic string. We quantize the closed relativistic string. We see how gravity emerges from the closed relativistic string. Then we're gonna see d-branes, and then we're gonna start doing thermodynamics with d-branes and strings and getting the black hole spectrum and being happy. So that's the plan for now. Cool. Okay, I'll see you later. Like and subscribe to the video. Meow.